You're listening to DTFHN for May 2nd, 2026. I'm your sedimentary layer host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where mass replying, actually, is considered a love language. Today's lineup is full of things hiding in plain sight, doing more than they look like. Let's crack it open. One commenter cut straight to the thing everyone's actually wondering. If you start real applications inside that VM, won't it just eat all 8 gigs you gave it? And yeah, that's the right instinct. But the numbers here tell a more interesting story than the objection suggests. Let's break this down to what's actually happening on the silicon. A macOS VM on Apple Silicon isn't emulating anything. It's running native ARM instructions on the same cores as the host. The virtualization framework hands the guest direct access to the hardware. And you can see it in the benchmarks. Single-core performance hits 98% of bare metal. 98. That's not a virtual machine in the way anyone over 30 remembers virtual machines. That's practically a rounding error. The GPU story is almost as good. 95% of host performance. The only real penalty is the neural engine, which takes a significant hit on half-precision and quantized workloads. But here's the engineering reality. macOS can route those tasks through CPU and GPU instead. And for most workflows, you'd never notice. Now the size question is where this gets genuinely elegant. Howard Oakley, who's been doing this kind of methodical Mac systems work for years, stepped the VM down to just 2 cores and 4 gigs of RAM. The system used 3.1 gigs. Safari worked. Settings worked. Everyday tasks ran normally. On a machine that fits in an envelope. The MacBook Neo ships with that A-series derived chip, 8 gigs of RAM in the base config, and people immediately asked whether it could host a macOS VM at all. The answer is yes, and it's not even close. You could hand half the machine's resources to a VM and still have a functional host underneath. The practical constraint isn't compute, it's storage. APFS sparse files mean a 100 gig virtual disk only takes about 54 gigs on the physical SSD. But you still want at least 60 gigs of headroom for macOS updates to work. On the 256 gig Neo, that's tight. On the 512, it's comfortable. What Apple built with the virtualization framework is genuinely impressive engineering. Near-native performance, minimal overhead, and it scales down to hardware configurations that cost as much as a nice dinner. Another commenter asked whether the Xcode simulator could finally run smoothly on lower-end hardware. And while that's a different code path, the underlying trajectory is the same. The floor for useful virtualization keeps dropping. The real story here is that the performance tax for isolation has essentially disappeared on Apple Silicon. A sandboxed environment running at 98% of bare metal on a machine with 2 cores and 4 gigs of RAM. That's the kind of systems work worth admiring. Now, making software run fast is one thing. Pause. Getting it out the door is another puzzle entirely. I need web fetch permission to pull the article content. Without it, I'll write the segment based on the title, comments, and what I know about Noctua's Chromax engineering. Let me draft it now. There's a number buried in Noctua's blog posts that most people will skip past. The company says their black Chromax fans can take years longer to release than the original brown versions. Years. For a color change. And the reason cuts deeper than anyone outside materials science would expect. Noctua makes what are arguably the best cooling fans on the planet. Their signature brown and beige colorway is legendary. Partly for performance, partly because it looks like it belongs in a 1970s living room. The Chromax.Black line exists because customers kept asking for the same fans in a color that wouldn't clash with every build aesthetic on Earth. Reasonable request should be simple. It is not simple. The fan blade is a precision-engineered polymer component spinning at thousands of RPM, balanced to tolerances measured in fractions of a gram when you change the material composition. And adding black pigment means changing the material composition. You change the mechanical properties, stiffness, density distribution, thermal expansion, vibration characteristics. A blade that was tuned over years of iterative testing now behaves differently. The acoustic profile shifts, the bearing interaction changes, the carefully optimized flow dynamics drift. Run this forward. Imagine you've spent 4 years perfecting a fan blade geometry that produces 2.3 decibels, less noise than anything else on the market at equivalent airflow. Your entire reputation rests on that margin. Now, someone hands you the same blade in a different polymer blend and says ship it. You can't, because if the black version is even marginally louder, marginally less balanced, marginally less durable. You've just told every customer that your premium pricing was for the color brown, not for the engineering. What Nopto is actually doing is revalidating the entire fan from scratch for each color variant. New mold flow analysis, new balancing verification, new acoustic testing, new longevity testing. The same process that made the original fan excellent run again, because the material is physically different. One commenter called this content marketing executed perfectly, and they're right. But it works because the underlying story is true. This is a company that treats a cosmetic variant as an engineering project. In an industry where most manufacturers would just dip the existing part in paint and call it a day. Nopto rederives the product from first principles. The brown fans aren't brown because of branding. They're brown because that's what the optimal polymer blend looks like before you add anything to it. The color is a byproduct of the engineering, and changing it means doing the engineering again. That's a level of integrity that's increasingly rare. Not just in PC hardware, but anywhere. That same commitment to doing the work right shows up in a new tool that's putting real data analysis power directly in your hands. What does it actually mean for software to respect you? That question has been rattling around computing since the very beginning. In 1969, when Ken Thompson and Dennis Ritchie built Unix at Bell Labs, they made a choice that shaped everything that followed. They made the system's internals legible. You could read the code. You could see what it did. You could change it. That wasn't an accident or a marketing decision. It was a philosophical commitment to the idea that the person using the tool should understand the tool. Mljar Studio sits in that lineage. And it's worth being precise about why. This is a local AI data analyst. Stacy and Chill Y. Something in 3D 的来了的他那外的有经过成长的，放你的规方桌面可以有这一些审美的快的七楼也路内的真闹，数字会的多少的怪，可慢慢越咋不说，心愿同所能做，去管每个的出书，入真大的位的别他。这个规也为属于的准备了考虑做许也赛，负担得大都同声。Let's pull this thread on the technical architecture, because the engineering choices here are the story. Running the AI locally means your data never leaves your machine. That's not just a privacy feature. It's a trust architecture. The notebook output means every analytical step is reproducible. You're not getting a black box answer from a cloud service that you have to take on faith. You're getting working code that you can audit, version control, and hand to a colleague who doesn't even need Mljar installed to read it. One commenter made the point that matters most. Data analysis is high risk without a human in the loop. Bad analysis costs real money. And this is where Mljar's design philosophy earns genuine respect. They didn't build a system that replaces the analyst. They built a system that accelerates the analyst while keeping them in the driver's seat. The AI proposes. The human verifies. The notebook preserves the full chain of reasoning. This is how open tooling should work. The code is right there. The data stays with you. The analysis is reproducible. Compare that to the cloud-based analytics platforms, where your proprietary data gets uploaded to someone else's infrastructure, processed by models you can't inspect, and returned as conclusions you can't verify. The craft here is in what they chose not to hide. Every intermediate step exposed, every transformation visible. In an era where most AI products compete on how much complexity they can obscure from you, MLJR competes on how much they can reveal. That's engineering that trusts its users, and users who are trusted tend to build remarkable things. Now, here's a delight that only programmers could love. Agent News need two environment variables just to say, put temporary files here. I have enough from the article text provided to write this segment. Let me write it now. I spent 3 years at a shop where our build system broke every few months because someone's machine had TMP pointing at a RAM disk and TMP pointing at a network share. 3 years. We never fixed it properly. We just added another check. That memory surfaced immediately when I saw Raymond Chen's archaeology of why Windows still ships with both TMP and TEMP environment variables in 2026. And the answer is exactly as absurd as you'd expect. The question nobody wants to ask out loud. Because asking it implicates decades of decisions. Is this? Why does any operating system in the year 2026 still resolve temporary file locations by checking two competing environment variables whose precedence is undefined? Pull this thread back to 1973. CP and Mljar had no environment variables at all. You configured your programs by patching bytes directly in the executable. Raymond Chen casually mentions that his WordStar manual told him which bytes to patch, and that there was scratch space set aside so you could handwrite assembly subroutines for your printer driver. Just sitting there with hex editor, making your word processor talk to your hardware. There's something beautifully direct about that. No abstraction layers, no configuration management frameworks. You and the metal negotiating. Then MS-DOS arrives in 1981, bolts on environment variables, and immediately nobody agrees on what to call them. Some programs check temp, some check TMP. MS-DOS itself picked temp for its pipe simulation. Since single tasking meant piping was just run program 1, dump output to a temp file, feed it to program 2. But that choice carried no authority over the ecosystem. The marketplace had already fractured. And here we sit, 53 years after CPM, still carrying both. One commenter nailed it. The moral is just make sure they point to the same path. That's a real engineering lesson buried in this history. When you can't fix the architecture, you standardize around the scene. Every system accumulates these little fossil joints where two competing conventions never resolved. They just calcified. What I love about this kind of digital archaeology is what it reveals about how systems actually evolve. Not through grand design, through accretion, compromise, and the quiet stubbornness of defaults that outlive every reason for their existence. The bones of CPM are still in your Windows machine. The disagreement between two environment variables is a 50-year-old argument that everyone stopped having, but nobody ever settled. The tools to fix this have existed for decades. The will to fix it never materialized, because both variables work mostly if you squint. And that, honestly, is how most infrastructure persists. Not because it's good, because it's good enough. Moving on. I have enough from the detailed README and the single reader comment to write this segment. Let me write it now. The strongest case against dashboard as code is that nobody asked for it. Dashboards are visual. They're the one place where drag and drop actually makes sense, where the spatial relationship between elements is the whole point. Turning that into YAML is like writing sheet music for a painting. You lose the thing that made it useful in the first place. And honestly, that argument held for years. Looker tried a code-first approach and ended up getting absorbed into Google Cloud, where it mostly confuses people. Metabase went the other direction, made everything point and click, and teams loved it. The visual tools won because dashboards are fundamentally a visual problem. Now run that logic forward. If dashboards are visual, then building them requires a human staring at a screen, dragging widgets, clicking through menus, which means every dashboard is a manual artifact, which means they don't version well, they don't review well, they don't compose well, and critically, they can't be generated by an agent that doesn't have eyes or a mouse. DTF is an open source tool from the Bruin Data team that defines dashboards in YAML or TSX, validates them and serves them from a single binary. Postgres, MySQL, Snowflake, BigQuery, Redshift, Databricks. The full lineup. There's a semantic layer where you define metrics and dimensions once and reference them everywhere. DAC generates the SQL. The TSX option is the quiet revelation here. YAML gets you static layouts. TSX gets you loops, conditionals, and load time queries that generate layout from the database itself. A dashboard that reshapes itself based on what's in the data. Try doing that in a drag and drop builder. But the real architectural bet is on the line buried halfway down the README. Built for AI agents to build dashboards in a reliable, unreviewable way. The project ships with bundled skills for Claude and Codex. Run DAC and Knit, and it drops agent skill files into your project. Chat with your dashboard, get it updated. Review the diff in Git, like any other code change. This is what code first actually unlocks. Not a worse experience for humans. A possible experience for agents. The drag-and-drop builders lock dashboards into a paradigm that requires a visual cortex. DAC makes dashboards into text, and text is the universal interface. Agents can write it. Humans can review it. Git can track it. CI can validate it. The whole thing is open source, Apache licensed, connections handled through Bruin's existing infrastructure. One reader noted the docs landing page could use that demo GIF from the README, which is the kind of feedback you only get when people are actually trying to use the thing. Builder energy. Ship it. Improve it. Repeat. Dashboard as code failed before because the tooling demanded more effort for less capability. DAC flips that by making the code layer the foundation that both humans and agents build on. The visual interface becomes a rendering target, not the source of truth. That's the inversion that matters. Moving on. I have enough from the article text and comments provided. Let me write the segment now. In 1996, the International Dark Sky Association published its first model lighting ordinance. It was 14 pages long. Most cities ignored it. Light pollution kept getting worse. Not because we lacked the science, but because the tools to demonstrate the science were locked inside proprietary lighting design software that cost thousands of dollars per seat. The people who needed to see what bad fixtures do to the night sky couldn't afford to run the simulation. 30 years later, a Rust developer ships a browser-based light pollution simulator that runs entirely client-side, uses real photometric data from actual luminaire files, and renders the results in a full 3D urban scene. No backend, no license key, No institutional access required. You load a streetlight profile, adjust the uplight percentage, and watch the sky glow grade shift in real time. From F, severe, down to A, excellent. Just by swapping to a full cutoff fixture, the difference shows up on the buildings, in the sky, everywhere the math says it should, because the math is actually driving the rendering. No fudging. That word choice matters. The stack is worth noting. 20 Rust crates handling photometric format. Iolun DAP, IES, Oxytech, the works. Bevy for the 3D engine. WebAssembly for browser deployment. About 1,000 lines of new code to wire the photometric library into the rendering pipeline. The whole thing parses lighting standards from the EU, the US, and China. That last one reverse engineered from translated PDFs, which tells you something about how accessible these standards are in practice. Now play devil's advocate for a moment. Does a browser demo actually change lighting policy? City planners don't make fixture decisions in web browsers, except the reason bad fixtures persist is that procurement committees can't visualize the difference. They see spec sheets with numbers. This tool turns those numbers into something a human eye can evaluate in seconds. That's the gap it fills. The comments reveal the usual web GPU friction. Safari bugs, blank screens on Linux. Which is the tax you pay for shipping on the bleeding edge of browser graphics? Those are solvable problems. The unsolvable problem was making photometric science accessible outside the lighting industry's walled garden. 20 open source crates on crates.io just solved it. 7 stories in, and we keep finding open tools cracking open closed worlds. Next up, pause. The T84 Evo. I don't have web fetch permission, but I have enough from the article text and comments to write this segment. Let me write it now. 50 years. Texas Instruments has been shipping calculators powered by the Z-Log Z80, a processor designed in 1976, the same year Apple was founded in a garage. The Z80 powered Pac-Man arcade cabinets. It ran CP/M, and until this month it was still crunching polynomials in American high school classrooms. The TI-84 Evo finally retires it for an ARM Cortex. And I want to feel something about that. I really do. Think of it like a cathedral. Notre Dame took 2 centuries to build, and every generation of masons worked with better tools, but kept the same floor plan. That's TI's graphing calculator line. New stone, same blueprint, same landlord collecting tithes at the door. The Evo gets 3 times the processing power. A color screen refresh, 7 candy shell colors with marketing copy that reads like a paint swatch catalog. Lavender for soft vibes with strong math energy, which is a real sentence a real human approved. But the architecture of control hasn't changed one bit. The comments on this one are a time capsule. Someone programmed a TI-85 in prison and built their first real software. Someone else's parents hid one in the attic for Christmas, and mice chewed through the packaging. Nearly every story follows the same arc. The math was forgettable, but the calculator was someone's first computer, their gateway to programming. That matters. And then the uncomfortable question, raised by multiple commenters. Show me a high school math problem you can't solve on a $12 Casio. Show me one. There are knockoffs for a single dollar that handle the same curriculum. The TI monopoly in American math education isn't a technology story. It's a procurement story. Standardized tests specify TI compatibility. Textbooks reference TI button sequences. The moat isn't engineering. It's institutional inertia dressed up as pedagogy. The Evo is a faster calculator inside a locked ecosystem. Meanwhile, a kid with a $5 microcontroller and an internet connection has more computing power and more freedom than any TI will ever offer. The tools exist. They just aren't the ones on the approved list. Tools on approved lists versus tools that actually work. Let's talk about someone making PDFs less painful with AI that runs right in your browser. Every PDF form you've ever filled out is a small act of surrender. You hand your name, your address, your social security number to some system, some server, some pipeline you can't see and didn't audit. That's the default. That's how it works. And most people don't think twice about it because what's the alternative? Print it out and use a pen? Simple. PDF built something worth examining. It's a demo right now, but the architecture is the point. You talk to an AI, the AI figures out which fields need what data, and it fills the PDF. Standard stuff so far. But the document never leaves your machine. The form parsing, the field mapping, the actual act of putting data into boxes. That's all client side. The AI sees your chat messages, yes, but it never touches the document itself. It issues tool calls. Structured instruction. And your browser executes them locally. This is a design pattern, not just a product. Client-side tool calling means you can separate the intelligence from the data. The language model reasons about what needs to happen. Your device handles the sensitive parts. The commenters caught this immediately. One person pointed out the chat messages still go to a remote server, which is true and worth flagging. But the roadmap is obvious. Swap in a local model, something running on your own hardware, and now nothing leaves the machine. The entire pipeline becomes sovereign. The first commenter said it plainly. I'm looking for exactly this once it's secure enough for real data. That's the gap. And it's a gap that local models are closing fast. Pull this thread further. Every form, every document workflow, every bureaucratic process that currently demands you upload sensitive data to someone else's infrastructure. All of it can be re-architected this way. Intelligence in the cloud if you want it. Execution on your device where you control it. The tools to build this exist today. Simple PDF just showed what the pattern looks like when someone actually assembles the pieces. And assembling pieces is exactly what's happening at the tooling layer too. Pause, let's talk about a clever new way to define AI skill. One commenter nailed it. A quote, "The obsession on token discounts recently is pretty funny. If you extrapolate far enough, you end up back to where we started, programming languages. That's the thread worth pulling. Because skill.make isn't retreating to programming languages. It's recognizing that we already solved dependency resolution decades ago. Make figured out directed acyclic graphs in 1976. 50 years of battle-tested execution ordering. And we've been asking language models to rediscover it from prose instructions every single time they run. The engineering here deserves appreciation. 5 prefix types, @ for shell commands, $ for tool invocations, question mark for reasoning steps where the model actually needs to think. Variables, conditionals, multi-line strings. The full makefile grammar repurposed as an agent control language. And because it's make-shaped, every target is auditable. You can git diff a skill change and see exactly which execution path moved. You can count invocations. You can trace failures to specific nodes in the graph. The token savings are real, but they're the least interesting part. 15% reduction across a full skill collection. Sure, some files drop 50%, but the structural win matters more. When you write a skill as a DAG, the harness resolves execution order deterministically. The model stops guessing what comes next and starts executing what's declared. That's the difference between a build system and a wish list. And it's MIT licensed. The spec is open. Any agent harness can implement it. No vendor lock, no proprietary skill format, no platform dependency. Just a pattern that works. published where anyone can use it. This is how open infrastructure gets built. Someone says, "We already solved this problem. Here's the format. Go build on it." Moving on. There's a number buried in this piece that deserves your attention. 250 times. That's the speed spread between the slowest and fastest cable that fits the same hole. USB-C is a shape. It is not a promise. Let's break this down to what actually happened. The USB Implementers Forum had one job: make a universal connector. And they did. Physically, every cable clicks into every port with the same satisfying snap. But behind that uniform rectangle, 7 different protocols are playing 7 different games. Your iPad Pro ships with a cable that runs 83 times slower than the port it plugs into. Apple, a company that will spend 4 years perfecting a chamfer, ships a cable in the box that bottlenecks their own hardware by 2 orders of magnitude. It gets better. The MacBook has 2 USB-C ports, side by side, identical to the naked eye. One is 20 times faster than the other. There's no label. There's no color difference. You just have to know. Or guess. One commenter described an office prank. Swapping which port a colleague's charger sits in, because only one of the 2 identical ports actually charges the laptop. That's the user experience of a standard with 6 name changes in 15 years. The USB-IF has renamed 5 gigabit per second, USB 4 times since 2008. Not because the technology changed, because the branding got embarrassing. When your standards body spends more energy on nomenclature than on clarity, the standard has become a liability dressed as convenience. USB-C is a universal connector, the way English is a universal language. Technically true, functionally a minefield. The shape is open, the protocols are a maze, and the cable in your box is almost certainly lying to you. This has been your daily tech feed for Hacker News for May 2nd, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go look a little closer at something you thought you already understood. We'll see you back here tomorrow.